Hello, everyone. This is Professor Jeff Wilkerson at Luther College with an introduction to Exercise 17 from Astronomers as Observers and Experimenters, published by Kendall Hunt. So this is an exercise and activity that's all about solar rotation and measuring the solar rotation. And so let's jump right into the ideas here. We'll get back and talk about some of the learning outcomes, some of the learning goals you might have for this exercise. But the idea is this. If this is the sun, and the sun is rotating, suppose that this part is coming out of the board toward you and this edge is rotating into the board, so that you see the sun rotating this way. You should see Doppler shift with our delta lambda over lambda, V over C is equal to delta lambda over lambda. You should see a red shift for this edge of the sun receding from you and a blue shift from this edge of the sun moving towards you. Now, one way to do that would be to try to measure that, to try to understand the rotational speed right here, would be to get just an image of the sun right here and an image of the sun right here, or just one of them probably is good enough, and to measure the recessional speed of the sun right there. But that's actually a little bit tricky to do. And so what we have in this exercise for you is a strip of the sun across there, taking the spectrum of that strip. So you'll see that at the point that's right here in the middle of the sun is moving across this direction in the model that we have drawn right here. And so there's no Doppler shift. There's no motion away or toward you, the observer. And so you just see an unshifted line right here. Delta lambda is 0 right here. Because remember, this is the radial velocity. It's the velocity, the component of motion that is toward the observer or away from the observer. Away from the observer toward the observer, across the line of sight, we would say, moving in this image left to right, neither away nor toward the observer. So you would see a line in the spectrum. So you take a picture of the sun through a spectrometer in a spectrograph. You would take that picture and you would see a line, and that line would be shifted, unshifted in the middle, and then it would be shifted on one edge of the sun a maximum amount. So you would be getting a larger and larger and larger red shift as you move this direction, and a larger and larger blue shift as you move this direction. Now your spectrum is going to have a bunch of lines in it, and you're going to see all of the lines shifted. And the beauty of this is, so here's a way to think about this. If we just took this picture of all of the sun across here, we would get one big thick line where the red shift and the blue shift were all mixed together. So some of our picture would be red shifted, some of our picture would be blue shifted, and some of it would be not shifted. And we would have what we would call a broadened line. So we would have, you could call this a Doppler broadened line. It's not quite what people usually mean, because they usually mean it's thermally broadened. They usually means the temperatures of the atoms moving around, the velocity of the atoms due to the temperature moving around when you talk about Doppler broadening. But this would be a kind of broadening due to the Doppler shift, where you're seeing all of these unshifted, red shifted, and blue shifted all mixed together. But because the sun, okay, think about this for a star. If you look at a distant star, we can't resolve the surface of the star. That's what you're going to see. You're going to see these broad lines. If the star is rotating very rapidly, you're going to see the red shift, the blue shift, and the unshift all together, the various shift, increasing shift, increasing shift to the other direction. All of that mixed together, so you get a thick line. But for the sun, it's close enough we can actually resolve the surface of the sun, so we can take a picture so that one part of our picture is this edge of the sun, the other part of the picture is this edge of the sun, and you see you move from one edge of the sun across the sun. And that's what you get, for example, in figure 17.3. It's just the one I picked up right there. So in picture 17.3, you see these lines that are from the spectrum of the sun, absorption lines. One edge of the picture, one edge of the spectrum up here is one side of the sun, and the other edge is the other side of the sun. The center of the sun is right there. Because we can resolve the sun and we can see the different edges, we see the line tilted that way. Do you see how those lines are tilted across there? So you'll see the red shift on one end and the blue shift on the other end. So this is the longer wavelength lines down here, shorter wavelength lines down here. We have a finder chart. These are atmospheric oxygen lines that you see, these vertical lines that are untilted. They're also relatively crisp. You see the broad wings on the absorption lines from the sun. And so if you can measure that tilt, you can figure out how much that wavelength was shifted. So one of the things clearly we want to be able to do, if you're thinking about learning goals for this, is we can say, okay, we measure that tilt, we see how much it was shifted, delta lambda. You can ask the question, how much is the top shifted one direction, how much is the bottom shifted the other direction? You got a red shift and a blue shift, one side of the sun, the other side of the sun. Presumably those velocities are the same, but it's conceivable that there could be some, you could imagine a model, I suppose, where there was a slowing down of the sun on one side and speeding up as it moved across. But this isn't what we would expect to see. So we would expect to see this recessional velocity be the same as the approach velocity over here, and that v would be here. And so you're measuring a delta lambda on one side, delta lambda on the other side. That is the how far the shift is from vertical that you would have right there, what that tilt is. So one way to do it, and the way that's recommended in the lab, is to say that if you've got a line that's tilted like that, if you just measure how far this edge is from this edge, what that delta lambda, call that your delta lambda over here. And that's actually associated with 2v because it's got the red shift and the blue shift both in there. This side is red shifted, this side is blue shifted. So the delta lambda from one side to the other side is going to be the delta lambda, the 2 times the rotational velocity, since it's got both the, it's got added in there twice. Okay, now it's also conceivable if you could find the center of that line, then you could just measure one of those delta lambdas. You can measure it out each way. So if you could figure out where the unshifted, that would be a possibility to do this lab. That would be one way I might be inclined to do this lab, is to find the very middle of this spectrum and their spectrograph right there, draw a dot right there, draw a vertical line, a line as vertical as you can through here, and see what the shift is either direction over here would be one possibility for doing this. Another possibility would be to draw a line. You've got your shifted line right there. You draw a line right through that, measure the slope of that line, and ask what is the slope of that line that you draw through the line in the spectrum, and say, okay, if I can measure the slope of that line, I can then calculate what delta x is across the width. What would delta x be across the width here? So that's actually a pretty good approach to doing this lab as well. A little different from what's written in the textbook, but there's alternate approaches. This is, okay. Let's do back up and talk about learning goals just a little bit with the exercise. There are a lot of learning goals associated. One of the learning goals that permeates all of the exercises, all of the activities in this book, everything you've been reading about, everything you've been watching me talk about here, is the idea that, it's right in the title, astronomers as observers and experimenters. Astronomers make decisions about how to take data, how to process data, what data set to take all of the time, and those decisions determine the outcome of a given experiment, of a given effort to understand the universe. So that's what you got going on there, is to say astronomers are making these observations, they're making decisions about this. And so that's one of the goals you could have for this activity, is to say we talked about these different ways of approaching, trying to understand what that shift is to get to that velocity. Which one do you think would work best? Which one would you like to employ? Would be one way to go about doing that, and understanding to say, okay, understanding that learning goal of making decisions to get the most out of a data set. So that would be one thing, one learning outcome that you might see in here that might be interesting for you. Another certainly is going to just understand the rotational speed of the sun. And then one of the things that's built into this exercise is we have these spectra that are taken at different latitudes. And so you can ask, well, okay, what would this spectrum be? What's the rotational velocity as a function of latitude of the sun? So you've got the spectrum at different latitudes of the sun. It turns out the sun's a differential rotator, so they're not all rotating at the same pieces. So just understanding that the sun is a differential rotating, that the different latitudes are rotating at different speeds, could be a learning goal for this activity as well. Better understanding of how to use spectra to make these measurements. this I should have at some point, and I should know. I could sit down. I think I could do it. I think I could pull it out if I sat down and did it, but I haven't done it. To add up all of the exercises in this book that rely on spectra and use spectra to determine velocities and use velocities to build physical models of a system. The number's high. And so, because we've talked about this use of spectra quite a bit as we've shot these videos, as we've done these introductions to these labs, and we're not even done yet. And so, the idea here is that we really want to understand how to use spectra. And one of the ideas that comes back again and again and again is this picture of the spectrum of the sun. This could have been printed to any scale we wanted. We could have printed this size or this size, or we could have blown it up and projected it on the wall and made it huge. So the actual shift of the line in millimeters on this picture is dependent both on the wavelength shift, the velocity of due to the rotation of the sun, due to the velocity of the sun's rotation, but also on just how we chose to print this picture, the scale of this, which we're calling the dispersion of the spectrum. So you can figure out the dispersion of the spectrum. As always with these activities, find two lines down here and measure the separation of those two lines of known wavelength. Use those oxygen lines, and then come up and find those same two oxygen lines up here and measure their separations on here. You measure on this spectrum, find the wavelength difference on this spectrum. Measure on this spectrum, find the wavelength difference, and you'll say, oh, a difference of this many millimeters on this spectrum would be equivalent to a wavelength change of whatever the difference is across here. So you take the wavelength difference in angstroms down here and divide it by the shift in millimeters, the separation in millimeters up here, and you get a dispersion that's in angstroms per millimeter. And if you have a dispersion that's in angstroms per millimeter, and you multiply your delta lambda that comes from the tilt right here by that dispersion, you're going to be taking angstroms per millimeter times some shift in millimeters is going to give you a delta lambda in angstroms, okay, that you can plug right back in here. So that's what you have to do with these things, is you have to measure the shift in angstroms. You have to convert the shift that you measured on your picture in millimeters to wavelength space, a delta lambda in angstroms, and then you divide by the rest wavelength, which you can read right off here, and you're good to go. Now, you have other decisions to make as you're doing this experiment, and that is to say, you'll notice the broad wings, they're a little bit hard to tell where the lines end and start for these solar lines because of the broadening out here at the edge that you see. And so think about what you want to do. Do you want to measure the left edge and the left edge, or the right edge and the right edge? Or do you want to measure a right edge and a left edge? What makes more sense to you when you're trying to think about measuring this tilt? Center and center, are you able to measure the center? Are you able to determine where the center is? Can you do that? And maybe. And how are you going to go about measuring that shift across there? If you wanted to, you could try to mark the center. That would be an idea. Try to mark the center down here and up here, and draw a thin line through the center and measure the line, or just mark draw a line, a vertical line from this edge, and mark that shift, measure that shift over there if you're doing left edge to left edge. As always, these shifts are going to be small and hard to measure, and so we like to use digital calipers wherever we can. So there's your digital calipers that I would use here to try to measure that shift in millimeters that we're going to convert to angstroms right here. So first job is to do this at the equator, and then do this at a couple other latitudes, and see if you can measure how fast the sun appears to be rotating. If you measured the slope, if you use this technique of measuring the slope of the line, you should be able to measure the recessional speed. Remember, you're measuring the speed, the radial velocity, the speed that the given piece of the sun is moving toward or away from you, and that speed's growing out here. It's not that the speed of rotation is growing. The material here is moving the same speed as the material there. What it's telling you instead is that the component that's moving away from you is growing as you're moving out that direction. So that's what we've got. Take a look at some of the other activities. Take a look at our introductions to some of those other activities that use the spectrum. Probably most importantly would be to look at the evidence of the Earth's revolution lab, where we talk about this idea of using spectra a lot, and start to understand, start to build a picture that you understand just how important spectral measurements are in astronomy, taking spectra and using those spectra to measure velocities and using those velocities to make a physical model of some system, in this case, the sun. Good luck with it, everybody. As always, if you have any questions, shoot me an email and ask me, and I'll see what I can do about it. Thanks.